Okay, so today we have Jasmin Brewer, who's going to tell us about measuring hard probe suppression without a measured PP reference. So Jasmin did his undergraduate in Colorado and her PhD at MIT, and she's now at CERN, and she's an expert in jet quenching and unrelated phenomena. Okay, so you can start when you're ready.
All right, thank you very much for the introduction and also for the invitation to give this seminar. Today I'm going to talk about some recent work on measuring hard probe suppression without a measured PP reference. And this is kind of a relatively general problem, but I'm going to be kind of specifically talking about it with reference to upcoming oxygen-oxygen run at the LHC. And this is going to be based on some recent work in collaboration with Alex Hoos, Alexis Mazaliauskas, and Wilco van der Schie, which appeared recently on the archive. And I'm very happy for lively discussions during seminars, so definitely feel free to interrupt me as you wish. So maybe one of the primary motivations, as I see it, for studying small systems, for example, oxygen-oxygen or proton-lead, is to really try to understand the intersection of high energy physics and heavy ion physics. So in proton-proton collisions, we have kind of a well-established and very successful framework of perturbative QCD for describing sort of the production of hard processes like hadrons and jets. On the other hand, in for example, heavy ion collisions like lead, and there's in some sense sort of a maximally different picture where sort of in addition to these kind of perturbative production, there's also sort of large numbers of rescatterings which create collectivity and sort of collective behavior in the soft sector, in addition, presumably, to kind of energy loss and suppression of these perturbative hard probes. And so by studying small systems, we can try to access sort of the turn on of these collective effects as a function of multiplicity. And this has become, I think, kind of very interesting recently with the observation of sort of flow-like correlations in small systems. So the flow correlations, for example, here, V2 and V3, which are sort of considered to be characteristic of collective effects in large systems like lead, have also been observed in sort of much lower multiplicity systems like proton lead. But on the kind of flip side of that, there's been no observation of the suppression of hard probes. So whereas in lead-lead collisions, there's a strong suppression in this case of the yield of hadrons as a function of PT, this substantial suppression is not seen in proton-lead collisions. And so the question is kind of to be addressed by studying small systems is to what extent these two observations of flow correlations, but the sort of apparent lack or smallness of energy loss in small systems are kind of consistent with some sort of collective effects in these small systems. And so kind of to try to sort of move towards addressing this question, one sort of potential avenue is an upcoming oxygen run at the LHC, and sort of to explore some of the unique opportunities of both oxygen-oxygen and proton-oxygen. We recently organized a workshop at CERN in collaboration with Alexis and Wilco, both sort of on the technical feasibility of running oxygen at the LHC, but then from the physics vantage point, maybe more sort of what unique opportunities oxygen provides both for the soft sector, for high energy probes like energy loss and nuclear PDFs. And then we also sort of explored the opportunities of proton oxygen for cosmic ray physics. And so there's actually sort of many kind of unique features of oxygen compared to, for example, proton lead, which we summarized in this document. But what I'm going to kind of focus on today is specifically high-pT probes and sort of what opportunities oxygen provides, both for sort of trying to discover energy loss in small systems and also for constraining nuclear PDFs. And so there were kind of maybe part of the motivation of studying hard probes in oxygen collisions is that there were recent sort of theory calculations suggesting that although energy loss is rather small in these small systems, that it may still be distinguishable from the baseline. And so what I mean by that is that here in blue is sort of a spread of kind of not unreasonable energy loss models compared to the nuclear PDF baseline in red. And so the hope is that by looking, for example, at hadron spectra at relatively low PT, that it might be possible to measure suppression of hadrons and or jets in oxygen collisions. But the problem that I'm going to kind of be talking about today is that in general, these kind of hard probe suppression measurements rely on a reference. And what I mean by a reference is like a measurement of the proton-proton spectra at the same energy as in this case, the oxygen run. And there's both theoretical and experimental reasons for this. So on the theory side, when you take some ratio, so this RAA, which is the ratio of the spectra in ion collisions to those in proton-proton collisions, then there's substantial cancellation of these PQCD uncertainties, especially scale uncertainties, which makes this baseline, the nuclear PDF baseline, more accurate. And then on the other side, there's also substantial cancellation of experimental systematic uncertainties, which can be made in these ratios that isn't the case in the absolute spectra. And so kind of the important point that I want to make is that in order to make accurate measurements of the suppression of hadron or jet spectra, in general, you have to take a ratio of those spectra with respect to a PP baseline. And this essential argument is important both for these kind of energy loss type measurements that I've discussed, which are relevant to OO, but also to a lot of the observables which put constraints on nuclear PDFs. And particularly for presumably relatively small energy loss effects in small systems, this precision of the baseline is really crucial for measuring these small effects. And so that kind of brings us to the plan for oxygen running at the LHC in Run 3. And at least roughly speaking, the plan is for 6 to 8 days total sort of commissioning and runtime for oxygen, and proton oxygen. And depending on the condition of the machine, there's kind of a couple of sort of options for the center of mass energy of the proton-proton run, which then kind of fix the default center of mass energies for proton lead and lead lead. So for example, if we have proton-proton collisions at 13.6 TeV, then we would have proton lead at 8 TeV and lead lead at 5.02 TeV. And there's plans to make proton-proton reference measurements at the same center of mass energies as the proton lead and lead lead runs. But with these same machine conditions, then you would have oxygen at something like 6.37 TeV and proton oxygen at 9 TeV. And so kind of the point is that there's additional substantial commissioning time that would be required to change the beam energy. So it would take more time for example, turn down the center of mass energy of the oxygen-oxygen run to 5.02 TeV, for example. But there would also be additional time to take a PP reference measurement at 6.37 TeV. So in a short run, it's likely that there won't be time to do either of these things. And in that case, it's likely that you wouldn't have measured PP reference either at the energy of oxygen-oxygen or at the energy of proton-oxygen. And so then is the question, you know, what physics can you try to do, especially with respect to these hard probes measurements in a short run without these PP references? And so that's kind of the basic question that we wanted to explore in this paper. So there's several kind of conceptual possibilities for a reference besides measuring it. So one, maybe the most naive thing that you can think of is to just try to construct a reference from theory or from data. And so the first thing that I'll kind of talk about is trying to construct these PP references from perturbative QCD. And then second, I'll talk about kind of a parallel way to construct the reference instead from measured data by trying to interpolate PP reference measurements at different energies to the necessary energy of the oxygen run. And so just for kind of conceptual clarity, kind of what I'll be imagining here is that you have a measurement of a PP spectrum at 5 TeV. And then we'll be trying to calculate the ratio of the 6.37 to 5.02 TeV PP spectra, which you can then rescale the measured data by. And this kind of ratio is important and interesting, at least partially, because many systematic uncertainties, either in the data or also in the perturbative calculations, will cancel in this ratio. And then finally, at the end, I'll kind of flash a little bit of another opportunity.
Hello?
Yeah.
Yeah,
Hey.
Can I make a question? Because, so there is proton-proton data for the LHC at many different energies, not only at 5.02, but you have from 900 GeV to 13 TeV.
Mm-hmm.
Well, I guess this was considered, but why not to use this whole set of data to do some interpolation? I mean, rather than extrapolation, because so what you are writing there, so what you have there is not an interpolation, it's an extrapolation, right? So if you have data at 0.02, then you extrapolate to something else.
So in practice, I'll talk about using 2.76, 5.02, and 7 TeV data to construct 6.37.
So this is data that was taken in the ion runs. So
yeah,
not in the normal proton-proton run. So there is some reason with triggers or something that made the other data not usable, or what is the reason?
Yeah, so I think the issue is essentially, so maybe I'll say two things about this. So the first thing is that we'll be using run 2 data just as an example because they don't have run 3 data. But there's substantial motivation to use measured data from the same run because that's how they cancel systematic uncertainties. So when they do the oxygen run in run 3, they would really like to use reference measurements, which were also measured in run 3 because the detector changes over time. And so using run 2 data to try to do the interpolation for a spectrum to use in run 3, they wouldn't be able to cancel as many systematic uncertainties. So I think that's kind of the primary motivation why we focus on 3 energies is because in run 3, then they would measure PP at whatever, 13.6 or something, and then PP references for proton lead and lead lead. And so kind of the most easy thing to do would be to use those three references, in which case you could hope for the cancellation of systematic uncertainties, rather than if you try to use older data like the 900 GeV, blah, 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 or like PP from other runs, or any of this data from run 2, then the experimentalists kind of complain that they kind of won't be able to cancel systematics because of the change of the detector between the different runs. Does that address the question?
Yes, thank you.
Okay, perfect. Great. So I'll elaborate a bit more on this, especially when I talk about the interpolation. So for starters, I'm going to discuss sort of what you can kind of do with perturbative QCD calculations, both for hadron and jet spectra in proton-proton collisions. And so kind of in sort of a perturbative QCD picture, then you can compute hadron and jet spectra directly. And essentially the idea is just that, if you have a cross section, then it's a convolution of parton distribution functions, in this case of the proton, with some partonic cross sections. And then in the case of hadrons, then you also have fragmentation functions, or for jets, you can have some showering or other sort of final state effects. And so we describe hadron spectra as a convolution of the PDFs with the partonic cross-section, the fragmentation functions, and jet spectra as a convolution of the PDFs and the partonic cross-sections. And then we'll also show some results of sort of showering effects on the jet spectra as well. And in this case, this μf and μr are unphysical scales, and then we use their variation to try to estimate the impact of missing higher order terms in the perturbative expansion. So the variation of μf and μr is going to be what I call scale uncertainties in the coming plots. So what we first did is to try to look at the comparison of the perturbative QCD spectra to actual measurements in PP before going forward and trying to calculate spectra which haven't been measured. And so here, these plots are a bit busy, but on the left, I'm showing hadron spectra at 5 TeV and the right 7 TeV. And the top are the spectra themselves. And then the bottom panel is the ratio of the spectra to the next to leading order perturbative QCD results. And so I'll just try to go through this in a bit of detail, but what you first see is that these measured data by Alice, which are shown in gray, actually don't agree very well, have about 20% differences with respect to the next to leading order perturbative QCD calculation. So that's what you see in this ratio. And the difference between the data and the PQCD is actually not even captured within the next to leading order scale uncertainty. So again, this is kind of the variation that you expect in the perturbative calculation based on the changes of the factorization or renormalization scales. And these kind of scale uncertainties, which are shown in blue, are large compared to like the PDF uncertainties, which are in red and orange. And the sort of story is actually quite similar also for 7 TeV. So again, you see that the data is about 20 or even a bit more % off of the measured spectra in Alice. But what's quite interesting is actually if you overlay the 5 TeV results on top of the 7 TeV results, then they essentially differ from the NLO expectation by the same amount. So it's kind of a curious feature that even though these sort of individual hadron spectra at these two energies are quite off, actually the ratio of 5 to 7 TeV is in quite good agreement with next leading order perturbative QCD. And so it seems that, whatever sort of systematic issues are impacting the computation of these spectra, the ratio actually seems to be in better control than the absolute spectra. For jets, the situation is, I would say, quite a bit simpler. So here I'm showing again kind of the same thing. So 5 TeV and 7 TeV jet spectra measured by ELISE and then also computed in Perturbative QCD. So again, here in the bottom panel is the ratio to NLO. And what you see is that the data, which are the black boxes, agree within uncertainties with the next leading order Perturbative QCD expectation. And this is both the case for sort of the partonic expectation, which is what we're dividing by, but also with when we include showering effects, which is what's shown in these blue data points here. If anything, it sort of captures some of the trend of the data at high-pT. And so this is kind of the case both at 5, and then we have a similar sort of story at 7 TeV, that the sort of, unlike the hadron spectra, at least within the uncertainties on the data, both the absolute spectra for jets and also their ratio is well described by next leading order PQCD. So with kind of this, I guess, cross-check in hand, then we can actually use Perturbative QCD to try to estimate this correction factor for QCD spectra. So what I'm showing here is the ratio of 6.37 to 5.02 TeV spectra for hadrons on the left and for jets on the right. And so what you can see here, so this essentially ratio is what you would use with, like, for example, measured 5 TeV data in order to try to construct a reference at 6.37 TeV. And what you see here is, at least if you, to the extent that you trust this ratio in the perturbative calculation, then the next leading order sort of scale uncertainties are dominant, at least at low PT. And we have a band of a few percent uncertainties on this ratio coming from perturbative QCD for hadrons. On the right, we show the same sort of computation for jets. In this case, sorry, was there a question?
No.
Okay, sorry, I heard something. Now we show the same ratio for jets. So the next leading order sort of scale uncertainties are relatively small, order 1% up and down. And for jets, we also had access to a next to leading order calculation, which agrees with the next to leading order calculation sort of within the uncertainties, within the scale uncertainties. And then the statistical uncertainties on the NNLO calculation. One interesting feature for jets is that you do see that these showering effects, which are shown in blue, can have a somewhat substantial impact on the spectra ratio, especially at relatively low PT, so below whatever 70, 80 GeV for jets. You may have some corrections which come from this showering to the next leading order results. So in principle, this would provide sort of a way to use perturbative QCD to construct a reference at 6.37 TeV using 5.02 TeV data. What I'm going to talk about next is sort of interpolation, which is kind of an alternative approach to trying to construct a reference based on measured data at nearby energies.
Jasmine, sorry,
Yeah.
before you continue, so this thing that you said that the quotient for the analog calculation as compared to the quotient for the data is just anecdotal for these two energies, or somebody has studied for a range of energies if this actually holds, and how big is that uncertainty? I mean, if you go back one more slide.
This one or the one about
Maybe one more that was
the hadrons?
So here you just show these two energies. So has anyone looked at more energies, and has anyone tried to quantify how good is this approximation of the quotient of the calculation with respect to the quotient of the actual spectra?
That's a good question. So I know that we were not the first ones to observe that PQCD doesn't do a very good job of describing the hadron spectra, the absolute hadron spectra. But then the second question is whether someone has sort of systematically studied how this depends on the energies. So there are also measured hadron spectra at 900 GeV, 2.76 TeV.
Because I mean, I see these plots, and sure, it looks nice. It looks like promising that the ratio of the calculation can be a good proxy for the ratio of the actual spectra, but it's anecdotal. I don't see. I mean, I would like to see more than just the comparison of two energies to actually believe that this is a good proxy.
Mm-hmm. Yeah, so I don't know of any sort of specific calculations in that regard, although that doesn't mean that they don't exist. But it is something that we could, in principle, do. So essentially just to do these NLO calculations also at 2.76 TeV, for example, and check that ratio as well. I think there's only sort of two other energies available, but it would provide, I agree, sort of at least more evidence if you see that trend for other energies as well. But we didn't do that.
Okay.
Any other questions?
No, you can go on.
Cool. Okay, nice. So yeah, so now I'll talk about kind of this alternative approach instead of PQCD to look at interpolation of measured data at nearby energies. And this is, so for example, in the proton lead pilot run, interpolation is what was used to construct PP references for the proton lead measurement. So this has been a technique which has been pursued in the past, but we try to kind of go a bit further on studying the uncertainties of this approach. So just to clarify, I kind of I was mentioning this in answer to a question earlier, but just to kind of clarify, what I'll be talking about is an example based on measured run 2 data at 2.76, 5.02, and 7 TeV. But this is purely an example based on the fact that we have access to these measurements and therefore can actually use the data. In run 3 for the actual application that we're hoping for this oxygen reference run, everything would have to be done with data measured in run 3. For example, something like 5.028 and 13.6 TeV. So this kind of the precise details of this interpolation should be taken with the grain of salt that it would be different energies which would be used for the interpolation in run 3. But we study sort of interpolation with these 3 energies with kind of the motivation that you would also use 3 energies in run 3. So essentially the kind of basic idea of all of these interpolations is to try to somehow describe the differential cross-section as a function of PT for these different hadron spectra in terms of some kind of fit, and then use that fit to use the beam energy dependence of that fit to try to interpolate to the spectra to a different energy. And there was a variety of work, I think starting in like 1975 or something, kind of arguing that you could get a basic type of description of these cross sections as a function of PT in this relatively simple form in terms of this sort of dimensionless variable xt, which is PT over root s, essentially, with a factor of 2. And then some kind of, in principle, dimensional coefficient, and then a power of this dimensionless variable. The precise sort of motivation of different functional forms isn't, I would say, overly well motivated. And so what we kind of study is trying to systematically vary the functional forms of these fits and study the dependence of the interpolation on those. So in something like the Proton-led run, at least in Alice, I'm not quite sure about in the other experiments, I think that, you know, they sort of chose one particular version of this type of functional form. So we consider this exponent n to have a variety of dependencies on this dimensionless quantity xt, as well as sort of some functions of root s, which generally we take to be either linear in root s or linear in the log of root s, and then study the dependence on the functional form. What's maybe less obvious, but actually turns out to be more important, is that more important even than the functional form of these fits is actually what data to include in the fits. And for hadrons, this is particularly important because hadron spectra are measured down to, 1 GeV, much lower than 1 GeV, where these kind of high-PT cross-section parameterizations aren't well motivated in any sense. And so what we'll take as kind of the default here is that you look at only hadrons above 7 GeV and jets above 40 GeV, but we'll also consider kind of the impact of changing these minimum PT cuts on the spectra to be included in the fit. So essentially the way that we do this is just to do a global fit of all of the PP spectra at these 3 different energies. And this is essentially based on maximum likelihood estimation. And the idea is quite simple, which is essentially just that for all of the different energies, then this is essentially, the likelihood function is essentially, just described as the difference between the fit and the data with a covariance matrix, and again, the difference between the fit and the data. And so if this covariance matrix is just, just has entries on the diagonal, then this is just a Gaussian, which describes sort of the likelihood that, that the fit is within the data within the uncertainties of the, in the covariance matrix. So I'll try to maybe make that more specific, but say that you have only statistical uncertainties on the data, then the covariance matrix is just diagonal with the square of those statistical uncertainties on the diagonal. And then this is just describing essentially a Gaussian where the likelihood of a fit given the data is proportional to sort of how far from the center of this Gaussian the fit is in accordance with the statistical uncertainties. I hope that gives some kind of intuition for what this form means. But essentially we take kind of two features of the covariance matrix. So we consider all of the statistical uncertainties to be just Gaussian on the diagonal. And then we also take the luminosity uncertainty to be fully correlated at each energy. And then we consider kind of essentially two cases. Either we have systematic uncertainties which are fully correlated between the energies, and then in the ratio, these systematic uncertainties cancel, and therefore we don't include them in the covariance matrix. Or we take the systematic uncertainties to be fully uncorrelated, in which case they just add on the diagonal of the covariance matrix in exactly the same way that the statistical uncertainties do. So essentially we try to kind of parameterize the two opposite ends of the spectrum. Either all of the systematic uncertainties cancel or none of them do, and try to kind of assess the sensitivity of these interpolations to those two cases. And so then of course, you know, if you do this maximum likelihood estimation, then you get some fit of the measured spectra. And so this is just kind of a sketch essentially of the data over the maximum likelihood value for Elise hadron measurements at 2.76, 5.02, and 7 TeV. And if you then kind of use these fits in order to interpolate the 6.37 TeV measurement, then sort of depending on the functional form, you get a variety of different fits. So here I'm showing, again, the ratio of 6.37 to 5.02 TeV hadron spectra on the left and jet spectra on the right for a variety of fit forms with kind of different dependence on this XT and root S are in the solid curves. And then the dashed curves are sort of different cutoffs for what data of the hadron or jet spectra we include in the fits. And what you can see is that sort of especially at low PT, the variation of the functional forms has maybe 4% uncertainties, but is also kind of systematically below the next leading order results. At relatively high PT, actually, the variation in what you choose for the minimum PT to be included in the fit is actually somewhat more important than the variation due to the functional forms, which is quite intuitive once you understand the problem, but is not maybe what we first expected. For jets, the variation in the functional form is quite a bit smaller. So the sort of total uncertainty, at least for fits which have reasonable chi-squared, which is the ones shown in solid, there's only kind of few percent uncertainties on estimating the jet spectra from these fits. But again, at least at high PT, there are at least order 2% deviations of these kind of data-driven results from the next leading order perturbative QCD calculation. So there's kind of some difference which you would get in the spectra based on whether you interpolate or whether you use perturbative QCD. So the next thing that we tried to do was to kind of assess what is the impact of these uncertainties on the measured data at the anchor energy, so at 2.765 and 7 TeV, on the interpolation. So you can clearly see from this plot that if you just take the maximum likelihood fit, then okay, you get one line, which here is at 1 sort of by construction, but there's rather large both systematic and statistical uncertainties on these data, which then isn't sort of incorporated in any natural way in the interpolation. And so the way that we dealt with this is to use a Markov chain Monte Carlo to sample the distribution of fits that are kind of consistent with the data within these uncertainties. And so just to kind of give some conceptual picture, essentially, if you do the sampling and then look at the posterior of the Markov chain Monte Carlo, then it gives you a distribution of fits, which are now shown in these light colored lines, which you can take, for example, the 2 sigma confidence interval on these bands in order to put confidence bands on the interpolation, if that makes sense. And so I think that we were kind of the first to study this particular method for how to assess the impact of the uncertainties on the anchor energies in the interpolation. And so we did this for 2 particular functional forms of the fits, which were kind of maximally different in terms of their maximum likelihood estimation, which are shown in red and green. So in red and green, we're showing these 2 different fit forms, assuming that you sort of fully cancel the systematic uncertainties in the ratio, and also that you use all of these 3 energies, so 2.765 and 7 TeV. And what you see is that even if all of the systematics cancel and you use all 3 of these energies, you still get relatively significant uncertainties coming from the statistical uncertainties, especially at high-pT. Particularly in the hadron spectra. For the jet spectra, it actually looks quite a bit better, where you have maybe 2% uncertainties kind of at all PT from this sort of interpolation, just arising from the uncertainties on the anchor energies. A quite interesting thing, at least for us, is that even if you're interpolating 6.37, you might say that the most important energies are just to have 5 and 7 TeV, since those are the closest ones. But actually what we found is that if you do the same fits except only with 5 and 7 TeV, the uncertainties are much larger. So there's actually important constraints which are put by including the 3rd energy in the interpolation. I think this is also somewhat what Carlos was suggesting earlier in one of his questions. And perhaps more obviously, of course, if you include all systematic uncertainties as being uncorrelated, then you'll also get larger error bands coming from the uncertainties of the anchor energies, which are then larger. And this has some impact on the hadron spectra, although is most obvious in the large systematic uncertainties on jet spectra at low PT, really cause a very substantial increase in the band from including only uncorrelated systematic uncertainties. So this is sort of just a summary of things that I've already showed you, but essentially sort of using these 3 different methods, we were able to kind of assess sort of the impact on the uncertainties of constructing a reference from a variety of different methods. So at least trusting the perturbative QCD results, we had sort of few percent scale uncertainties on the hadron spectra. Also few percent uncertainties from the fits, at least at low PT, but we noticed that there's sort of a systematic deviation between the next leading order results and the hadron spectra interpolation at low PT. And then when we kind of include the impact of uncertainties at the anchor energies, we get maybe, few to 5% uncertainties, even if canceling the systematic uncertainties. And for jet spectra, we also found kind of across the board, both in PQCD from the fits and also from the Markov chain Monte Carlo, sort of few percent uncertainties, with some deviation between the next leading order results and the fits, especially at high PT for the jet spectra. So this is kind of a summary of what we get by trying to construct these spectra in different ways. The final thing I kind of want to advertise is that it may not necessarily be necessary to have a reference, have a PP reference at the same energy. And so, sorry, was there a question?
No.
Okay, perfect. So the essential idea that we want to kind of emphasize is that it's actually the nuclear PDFs, not sort of proton-proton spectra themselves, that are the correct baseline for having no energy loss. And so in some sense, the reason that we needed this PP baseline was just to cancel uncertainties, not specifically because the ratio with respect to PP should be 1, because it's really this nuclear PDF baseline, which particularly for small energy loss effects is kind of the correct comparison to make if you're searching for energy loss in oxygen-oxygen collisions. And so the point that we kind of want to make is that you can also take, instead of constructing a PP reference at the same energy as the oxygen-oxygen run, you can also just take the ratio of oxygen-oxygen at some beam energy to PP at a different energy. And actually what we found is that there's comparable uncertainty cancellation, at least on the, well, I think both on the theory side, and we expect also on the experimental side, between taking OO over PP at different energies with respect to taking them at the same energy. So here, just as an example, we're taking the oxygen-oxygen spectra at 6.37 TeV and taking a mixed energy ratio with respect to PP at 5.02 TeV. So this would be an alternative to constructing a PP reference at 6.37 TeV. And what we find is that the next to leading order sort of scale uncertainties of the perturbative calculation are quite small. But what's large and important for oxygen are the nuclear PDF uncertainties. And so this is not specific to this mixed energy ratio, but is also the case for the ratio at the same energies. And this is right. So essentially, with these calculations, actually sort of the perturbative calculation of these mixed energy ratios is under quite good control. But the nuclear PDF uncertainties are still large. And this is the case both for hadrons as well as for jets. And so this kind of emphasizes the importance of proton oxygen measurements in run 3 for constraining nuclear PDFs if you want to kind of measure small energy loss effects in oxygen collisions. So just to kind of...
Hi, Jasmin, may I interrupt you? Can you
Yes,
go back
please.
to the previous slide?
This one?
Yeah, so,
Yes.
I mean, the good thing of having the ratio of the hadron and PP at the same energy is also that you cancel proton PDFs and fragmentation functions. And here you have different energies, so the cancellation is not that clear. So what is the effect here of you don't show the uncertainty coming from the proton PDFs, and especially for the fragmentation functions, because we don't know much about fragmentation functions. And actually, I think it's what is driving all this mismatching between the perturbative calculation and the data in the case of the hadron. So what is the uncertainty coming from that in this case? Have you looked at that?
Right. Yeah, so we did look, so the proton PDF uncertainties are essentially negligible here. And it's a very good point, and kind of, I guess, the point that I sort of wanted to make, which is that it's not obvious, like, you know, the advantage in the perturbative calculation, as you were saying, of taking the ratio at the same energy is that the scale uncertainty cancellation is better and the proton PDF uncertainty cancellation is also better.
Yeah.
But what we kind of want to emphasize is that this cancellation would be somewhat better if you took the ratio at the same energies, but it would still be the case, like even in this case, the scale uncertainties are very small compared to the NPDF uncertainties, and it's the same for the proton PDFs. So the point that we kind of want to make is that, you know, what doesn't change much is that the perturbative calculation, the cancellation is good enough, even at these two energies, that it's really only the NPDF uncertainties that are dominating. So the motivation to take the ratio at the same energy from the theory side isn't really clear, because you would still have dominant NPDF uncertainties, and you would maybe shrink slightly these like NLO scale uncertainties, or like you were saying, shrink slightly the proton PDF uncertainties. But since you're kind of overwhelmed by these NPDF uncertainties, you would have to kind of put a lot more constraints on the nuclear PDFs before the decrease in the scale uncertainties would kind of help you much, I guess. Does that kind of clarify the...
Yeah, I agree. The nominal is the nuclear PDF, so you don't care about the others. But I'm still a little bit worried, especially for the hadron case, because of the fragmentation functions. Because even if you get that the uncertainties are small, the fact that you cannot reproduce the hadron spectra is probably due because the fragmentation functions are not correct, basically.
Yes.
And well, I would be more happy with the jets, that you don't have to care about the fragmentation functions. But well, I guess that we need better nuclear PDFs, but if we are not going to have a PP reference for the PO measurements, it's also going to be difficult to improve a lot the nuclear PDFs. So
yeah, so one...
Something? Oh, sorry.
Yeah,
sorry.
No, yeah, so you're only looking to these two particular observables, but there are other observables that constrain nuclear PDFs, in fact. And these observables are not very good in constraining nuclear PDFs. The problem with the oxygen, of course, is that for light nuclei, we have a lot of a lot of uncertainties because there is no data. So Petya is here, only he's more silent than me.
Okay. I see, I didn't see Petya.
So he's also going to comment. So unfortunately, we have to come here to the microphone. I don't know, we have this setup in here. Anyway, so the uncertainties for the oxygen are large because there is few experimental data that constrain, in particular, gluons for light nuclei. Basically, there is no data. However, you can constrain this gluon distribution, for example, with other sets of data, with other observables at the same energy, oxygen, and I guess that Petya has some ideas. For example, I guess dijets or C plus W bosons. I don't know what is the luminosities here. Maybe you can comment more.
Yeah. So, well, the obvious one are the dijets, which we have been studying more intensely, and probably from there we can constrain with the available luminosities. So for any kind of electroweak measurements, I think with this short run, it's just not possible to get.
This is oxygen.
So, right.
So if you have, what you're saying is that if you have oxygen, and proton oxygen, then proton oxygen will constrain the nuclear PDFs with the digest, and then you can use it here.
Yes. Yeah. And also, as was discussed by Carlota, in the case of proton oxygen, we don't have the proton baseline at the same energy, but similar techniques of taking a mixed energy ratio can be used, and I have some results which I try to get public soon. So, and it seems like the mixed energy ratio is working very well in this case as well.
That's great news.
Yeah, because the first data we used, we didn't have the proton-proton reference. Right?
But so in the first data you used, you were using backward to forward ratios, right?
Yes.
And now you change, or you're still using backward to forward ratios, or you're planning to, like for the oxygen run?
No, in the case of forward to backward ratios, the problem is that you don't have as good locality in the nuclear X. You are always measuring like the correlations between large and small X, and by using a rapidity dependent measurement with the mixed energy ratios is probably better.
Okay, I see.
Okay, great. Yeah, that's very good news. I definitely look forward to seeing the results for the mixed energy ratios for proton oxygen. I guess it's, at least for us, seems clear, I think, from these plots that, that the proton oxygen sort of maximizing the utility of the proton oxygen run for constraining the nuclear PDFs is also quite important issue for hopefully measuring some energy loss effects in oxygen.
Jasmin, what are because the question here is whether you need nuclear PDFs at the 5% level or 10% level or 1% level. Have you quantified the effect of energy loss in oxygen?
So this was not a paper with me, but my collaborators and sort of the rest of the CERN group before I got here had this paper on at least hadron energy loss in.
I remember that. Yes.
And so I have this plot somewhere earlier. At least what they showed is kind of, okay, well, you can argue about the reasonableness of the variety of models that they chose. Maybe this band is wider than necessary, but they found kind of, depending the confidence intervals that you take on this band, maybe 5% effects or something at low PT in hadrons, if you really want to sort of rule out the possibility of any of these models. But I think it's probably something which more theory calculations maybe should also put input on, because this is only one set of particular calculations for that. But they did kind of try to vary the assumptions of the energy loss models in order to get this band. Does that answer the question you were asking?
Yes, thank you. Thank you, yes.
Okay. All right. I don't know that I have much more to say, and I imagine that my time is pretty much up. So just to kind of, yeah, my time is definitely up. Yeah, so just to briefly summarize, we explored sort of constructing a reference in perturbative QCD or using this interpolation, and in either case kind of found few % uncertainties, but it's kind of an important point that doing the interpolation or doing PQCD doesn't give you exactly the same results. And also Carlotta and others brought up the important point of the fragmentation functions for the hadrons that you may not actually sort of fully trust, especially PQCD for hadrons in this regime. And then also kind of briefly discuss just taking the ratio of OO and P measurements at different center of mass energies. And, you know, it's sort of important information going forward, you know, both to what extent the experimental systematics can be canceled in these mixed energy ratios, as well as kind of the issue that we were discussing with Petya of whether these mixed energy ratios can also provide important constraints in the proton-oxygen run. So with that, I guess, thank you for your attention. And
Okay, thank you very much. Do we have more questions? I don't see any from the people here. Maybe we have some from the virtual audience. So, well, I don't see any. So since we have a lot of discussions during the talk, I think we can stop here. So thank you very much again for accepting the invitation and for the very nice seminar. So,
thank you very much.
thanks a lot, Jasmin.